The last chapter that we will cover this summer, is chapter 7, which deals with rational expressions. Okay? A rational expression is really nothing but a fraction. It's just that in this chapter we're dealing with fractions that may contain a polynomial in the numerator and a polynomial in the denominator. So here the definition states that a rational expression is an expression that can be written in the form P over Q. So capital P over capital Q, where P and Q are polynomials and Q is not equal to 0. Okay, the Q is not equal to 0. Meaning, just as in any other fraction, your denominator cannot equal 0 if that particular fraction or rational expression will be defined. Remember, if the denominator is 0, then the expression itself is undefined. Okay, hold on to that thought. We will get back to it in a couple of minutes. So here on this screen are a few examples of rational expressions. Negative 2/7 is a rational expression. It's just a regular fraction. 3y cubed over 8 is a rational expression. Negative 4p over p cubed plus 2p plus 1 is a rational expression. And 5x squared minus 3x plus 2 over 3x plus 7 is a rational expression. All of these are rational expressions, just examples of them. Now remember that in general, for any fraction, if you have a negative a over b, that equals, it has the same value as a over negative b, which in turn has the same value as the opposite of a over b, as long as b is not equal to 0. So notice what's happening with the negative sign. The negative sign, if the numerator or denominator has a negative sign, then what it's saying is that you can move that negative sign from the numerator to the denominator, or from the denominator to the numerator, or you can move the negative sign in front of the fraction. So when you get to an example like negative 2 over 7, or the opposite of 2 over 7, another way you can write it will be negative 2 over 7, which is equal to 2 over negative 7. So that's 3 different ways of writing the same thing. Now look at the next example. I want to show you what can be done with this negative sign. The negative sign can be applied to that whole numerator. Look at it. It can be like this, basically distributed to the whole numerator. You see what I did? I took the negative and distributed to the whole numerator. Or you can say, well, leave the numerator as it is and bring the negative to the bottom. Look at it. Make sure you understand that they all mean the same thing, just by virtue of the placement of the negative sign. Now, to find the domain of a rational function, this is a concept that you may or may not have heard of before, but so pay close attention. The domain. Well, as with any fraction, a rational expression is undefined whenever its denominator is 0. For instance, in a regular fraction, you should already know that something like 3 over 0 is what we call undefined, because the denominator is 0. Well, in a rational expression, if you have a denominator, let's say you have x plus 2 over x minus 3. Here, your denominator is not 0 because it contains variables, but any number from the number line can be placed in the value of x, in the place of the x. But when you place a number in the value of x, and that number creates a situation where the denominator is a 0, then that number is not part of the domain. In other words, look at x plus 2 over x minus 3. What value of x would make the denominator a 0? In other words, if you take x minus 3, what would make it equal to 0? What would make that denominator equal to 0? What value of x? Well, that would be, if you add 3 to each side, x equals 3. You can almost look at it and see that if you plug a 3 in for x, what is the denominator going to be? I don't care what the numerator is. The numerator will be 3 plus 2, because if x is 3, then you plug in a 3 for x. But if you put a 3 in the denominator now becomes 0, which means that this particular rational expression is not defined when x equals 3. So it means that any other number you put in for the value of x will be a good replacement value, but 3 cannot be a replacement value for this particular expression because that creates an undefined expression. Now, every number on the number line is a solution, is a replacement value in the domain of this particular rational expression. But one way we write this is the domain. Let me just come over here. The domain of this expression, we write it in this manner. We say the set of all x such that x is a real number and x is not equal to 3. That's how you read it. The set of all x such that x is a real number and x is not equal to 3. This is the way it's read. Once again, it's read the set of all x. That's what those initial the initial brace, the initial brace in x is read the set of all x. The vertical line that you see after the x is read such that, and then you read the rest of it. X is a real number and x is not equal to 3. So what we're going to do is, when we're given a rational expression and you're asked to find the domain, what you're going to do is take the denominator and set it equal to 0 to find out what values will cause the denominator to be equal to 0. Sometimes that will be one value if the denominator is just a linear expression, or sometimes it will be 2 values in the case of a quadratic expression in your denominator. Watch what happens. It'll make more sense after you do a few. Now let's find the domain of each rational function. Look at this first one, 4x to the 5th minus 3x squared plus 2 over negative 6. When you're looking for the domain, you're looking for every value that will cause this expression to be defined. In other words, you want to know what values will make the denominator 0, and you want to exclude those values from your list of numbers. Now, is there a way, looking at this first one, is there a way is there even a variable in the denominator? There's no variable in the denominator. There's no place to put a number to even try to make the denominator a 0. So when you have a number, a constant in your denominator, then every number on the whole number line is part of your domain. So you would write the domain is the set of all x such that x is a real number. So that means every real number is in the domain, because there's no way to make that denominator 0, because I don't have any variables to put there. If there was a variable there, then we'd have to work it out to figure out what that value is that would make the denominator 0. What about this next one? What value of x would make the denominator 0? We are not concerned about the numerators at all when finding the domain. We're only worried about what makes the denominator 0. So let's take x plus 3 and see what makes it 0. What makes that a 0? Well, if you solve it, you get x equals 3. Well, 3 is the only number that you can plug into that denominator to make it a 0. Nope, negative 3. My bad. Negative 3 is the only number that you can plug in for x. You see, if you put a negative 3 there, then you have negative 3 plus 3. Doesn't that equal 0? Well, any other number you put in there for x is not going to create a 0. The only number that's going to create an undefined expression is negative 3. So we write the domain is all x such that x is a real number and x cannot be equal to what? Negative 3. So x is a real number, but x is not equal to negative 3. That is the domain of this particular function. Let's find the domain of this expression. X squared minus 5x plus 6. Well, when finding the domain, we're only concerned about the denominator. We want to know what makes the denominator equal 0. So let's take it, the denominator, and let's set it equal to 0. What's going to make it 0? This is a quadratic equation, so we factor. Okay, x and x. I need two numbers that multiply to positive 6 but add to negative 5. That's negative 2 and negative 3. So we have x minus 2 equals 0, or x minus 3 equals 0. So x is 2, or x is 3. So 3 and 2 are the values that if you plug them into the denominator, you're going to get a 0. So we have to write the domain now. The domain, all x, the set of all x such that x is a real number. And yes, you have to go through this. You have to write it. A real number, and x is not equal to 2, and x is not equal to 3. Only 2 and 3 would be the values that would make the denominator 0. Let's look at the next one. Want to find the domain? Set the denominator equal to 0. So we have x squared minus 3x minus 10. So what makes that a 0? Set it equal to 0 and then solve the equation. I have x and x, and I need two numbers that multiply to negative 10. So negative 5, positive 2. So we have x minus 5. Equals 0, or x plus 2 equals 0. So we add 5 to each side. So x equals 5. Here we're going to subtract 2. X equals negative 2. So the domain is the set of all x such that x is a real number. You can even just say x is real and x is not equal to 5. X is not equal to negative 2. So in this example, let's find the domain. X squared minus 9 over 4. Well, remember, when you're looking for the domain, you find out what will make the denominator equal 0. What value of x would make the denominator 0? Well, in this case, there is no x in the denominator. So there's no value of x for which this expression is not defined. So you have to look at every single number in the number line and say, well, the domain is all x, or the set of all x such that x is a real number. There are no limitations. They're all real numbers. I don't want to write it like that. X is a real number. A real number. There are no limitations, okay? There are no restrictions. There are no excluded values. So the domain here is all real numbers. Now, let's look at the next section, which involves simplifying rational expressions. Simplifying rational expressions is nothing more than reducing fractions to their lowest terms. So what we're going to do is look at this fundamental principle of rational expressions. It says for any rational expression, P over Q, remember P is a polynomial and Q is a polynomial. And if you have another polynomial R, where R is not 0, then P times R over Q times R equals P over Q times R over R, which is simply P over Q times 1. And all this is saying is that if you can factor your numerator and denominator, and there are two factors alike, a factor in the numerator and a factor in the denominator that are alike, you can cancel those out and they will form a 1. Okay, so in other words, let's look at a simple example of 15 over 65. You probably will understand it if we write 15 as a product of prime numbers. So 15 is 3 times 5. 65 is 5 times 13. Okay, now look at the 5 in the numerator and the 5 in the denominator. Well, what happens then is that they can cancel and it forms a 1, right? So then what you're left with is 3 over 13. So the same thing works when you are trying to simplify a rational expression that has polynomials in it. Look at this next one, x squared minus 9. That's a difference of 2 squares. So if you factor it, x plus 3 times x minus 3. Then if you factor the denominator, we look for two numbers that multiply to -6 and add to +1. So that's going to be plus 3 minus 2. Notice what we have here. We have a factor in the numerator of x plus 3 and a factor in the denominator of x plus 3. So they cancel to become ones, right? Now make sure you understand that you're canceling the whole binomial. The x plus 3, they're married. They go together. You're canceling the x plus 3 with the x plus 3. You're not canceling the x with the x and the 3 with the 3. Be careful. I'm going to use that word married. The x plus 3 are married. You can't cancel one term in that expression without canceling the other. You have to cancel the whole thing. So what you're left with in the simplified form is x minus 3 over x minus 2. So what I'm saying is, once you get this expression here, you cannot cancel these two x's in this last expression that I just wrote. You cannot cancel those because they each are part of a couple. Okay? They go together with the other term. Now let's simplify a few more. This is all we have to do. Factor the numerator, factor the denominator, and cancel what can be canceled. Okay? Completely factor the numerator and denominator. Divide out factors common, removing the factor of 1. So, look at the top. The top really is nothing but a 3 times y cubed. But look at the bottom. We can factor out a 3y cubed, and we will be left with a 2y minus what? 1. Now look at what do you have in the numerator and the denominator that are common. Okay? The 3y cubed and 3y cubed cancel, but they both become 1s. Be very careful that you put the 1 there, otherwise you will think there's nothing left at the top. But there is the 1. But it's 1 over 2y minus 1. Now based on what I just told you on the last slide, can I cancel this 1 with that 1? Absolutely not, because the -1 at the bottom is married to that 2y. Okay? You cannot cancel that, and you cannot reduce it any further. Okay? So I told you in this chapter we're going to be doing a lot of factoring. So honestly, when in doubt, just start factoring. Here we're simplifying. The instructions will read, simplify this rational expression. And in order to simplify, you factor the numerator and factor the denominator. Well, I'm going to go off to the side and factor this. And because I'm not going to take the time on this video to factor all of this out, I'm going to go off to the side and factor it. You can go off to the side and factor it and come back with whatever you have. Okay, after factoring, 5x minus 6 plus 1 factors to x minus 1 times 5x minus 1. And then the denominator factors to x minus 1 times 3x plus 7. So what cancels? Notice the numerator and denominator have an x plus 1 in common. Those cancel and become 1. So the simplified expression is 5x minus 1 over 3x plus 7. All right, look at this one. 5z to the 4th over 10z to the 5th minus 5z to the 4th. So we have 5z to the 4th numerator. And then the denominator, we factor out a 5z to the 4th, and we're left with 2z minus 1. And the 5z to the 4th cancels with the 1 in the denominator, so those both become 1s. So you're left with 1 over 2z minus 1. Notice the 1s cannot cancel. Okay, 5x squared plus 13x plus 6 factors to x plus 2 times 5x plus 3. The denominator factors to x plus 2 times 6x minus 5. Okay, I'm not here anymore to show you how to factor. That was the last chapter. Now the x plus 2's cancel, and you're left with 1s there. So the simplified expression, 5x plus 3 over 6x minus 5. You cannot cancel anything else. Okay, now when you have a numerator and denominator and they are opposites of each other, then the expression simplifies to -1. That means if all of the terms in the numerator are the same as the ones in the denominator except their signs are opposite, every term has an opposite sign of the one that's in the numerator, then you know they differ only by a factor of -1. So the expression simplifies to -1 when they are opposites. Now this first example I'm giving you has 2 plus x over x plus 2. Well, in this case, the 2 is positive in the numerator and the 2 is positive in the denominator. The x is positive in the numerator and the x is positive in the denominator. So you could actually write them both the same way. You could write x plus 2 over x plus 2 only because they're both positive. Okay? Only because they're both positive. And in this case, what happens with x plus 2 over x plus 2? Remember, they are married. They go together. So you can't cancel the x with the x. You have to cancel the whole expression at the top with the whole expression at the bottom. So it simplifies to 1. But look at the next example. It's 2 minus x over x minus 2. Look at the top and the bottom. Each term is different, is the opposite. Every term in the bottom is the opposite sign of the same term in the top. 2 is positive in the top, negative in the denominator. X is negative in the numerator, positive in the denominator. So what it actually says is if you basically factor out a -1 from one of them, then that's what you're going to be left with. For instance, let's factor out a -1 from the top. That makes the 2 negative and the x positive. All over x minus 2. But now look at the numerator. See, this x is positive. Now this x is positive. This 2 is negative. This 2 is negative. So they're the same now. So once you cancel all of that, you have left, I'm trying to erase it gently. Let me erase all of this. Once you cancel it, all you're left with is a -1. So if I factored out a -1 and I made that a -2 plus x all over x minus 2. Notice now this cancels with that, and what you have left is -1. Well, you don't really have to go through all of that if you recognize that they're opposites of each other. You can just say, well, they only differ by a -1. Look at the next one, 5 minus x over x minus 5. That simplifies to -1. Okay? Depending on the sign. So here we have 5 plus x over x plus 5. They are exactly the same thing. Both terms are positive. So x plus 5 is the same as 5 plus x. So it's just like saying anything divided by itself is 1. Now look at this one. Simplify this one. Well, before, it's probably easier to see if you just rewrite this as -3x squared plus 3. Notice what I did. I just rewrote it. Okay, and put the sign, put the x squared term first. But I want to factor the denominator. And I'm going to go back and factor the numerator in a second. So we get x and x plus 2 minus 1. But look at the numerator. I don't want that I don't want the leading coefficient to be negative, so I'm going to factor out a -3. Sometimes you got to work it out a couple of ways to just to see what's going to happen. Factor out a -3, and that leaves me an x squared minus 1. But that's a difference of 2 squares, right? Isn't x squared minus 1 a difference of 2 squares? So I'm going to come down here and factor it out some more. X plus 1, x minus 1, all over x plus 2 times x minus 1. So what do the numerator and the denominator have in common now that they are fully factored? They have an x minus 1 in common, which leaves 1's there, which means we have a -3 times x plus 1 over x plus 2. All right, let's simplify this one. What do we get? Let's try it. I'm doing it for the first time myself, so let's see. Factor out a 3, and we have x squared plus 2. And I see at the bottom a 4-term polynomial. I'm going to group those. Let me come down here at the bottom and group those. Let's see if I have x cubed minus 3x squared. Group that. And I'll have 2x minus 6 grouped. And then that will give me, can factor out an x squared. That will give me x minus 3. And here I can factor out a 2, and it give me an x minus 3. So I have x minus 3 times x squared plus 2. That's what the bottom factors to. So it factors to x minus 3 times x squared plus 2. But what cancels with that in the numerator? The x squared plus 2 cancels, right? So that factor cancels with that one. They both become 1's. And it leaves you, the simplified form only has a 3 in the numerator and an x minus 3 in the denominator. Now, can the 3 in the denominator cancel with the 3 in the numerator? No, because x minus 3, they are married. Okay, so we've simplified that. This one works pretty much the same way. Let's see. We have factor the numerator, factor out of 5. We have z squared plus 2. I'll go off to the side and factor z to the third minus 3z squared plus 2z minus 6. I'm factoring by grouping because there are 4 terms. I'm going to factor out a z squared. That leaves me a z minus 3. And I'm going to factor out a 2, and it leaves me a z minus 3. So we have z minus 3 times z squared plus 2. That's the denominator. Z minus 3 times z squared plus 2. What cancels? The z squared plus 2 and the z squared plus 2, which become 1. And we have 5 over z minus 3. And that is the simplified expression. 5 over z minus 3. Now, we're going to talk about writing equivalent forms of rational expressions. I've already alluded to this earlier. If you have a fraction where you have a negative sign, that negative sign can go either with the numerator or with the denominator, but not both, or it can go out in front of the whole fraction. Let me show you what I'm talking about when I say list the equivalent forms of this particular expression. Negative, or the opposite of 3x plus 7 over x minus 6. I can take that negative sign. I can take that negative sign and say I'm going to put it with the whole numerator. But because the numerator is married, the two terms are married, I have to include the parentheses. So I just put the numerator, the negative sign with the numerator, right? Or I can take it further and distribute the negative sign to the numerator. So the negative will go with the 3x and the negative will go with the 7. I just distributed all over x minus 6. Or I can take the negative sign and put it with the denominator. I can write 3x plus 7, but change the negative sign to go with the denominator, x minus 6. But because they're married, I have to put the parentheses. Now I can take it a step further and distribute the negative to the terms in the denominator. Okay, you see what I did? I took the negative and distributed. So honestly, all 5 of these expressions are saying the same thing. Okay? All 5 that I have equivalent to each other are saying the same thing. All right? So look at this one. We can go negative and then x plus 3 over 6x minus 11, which is also equal to negative x minus 3 over 6x minus 11, or it's equal to x plus 3 over the opposite of 6x minus 11, which is then equal to x plus 3 over negative 6x plus 11. That's 5 ways of writing the same thing. Go back and review. You need to know that if you have one answer and the problem has another answer, you need to be able to look at them and compare to make sure your answer is saying the same thing.